Okay, very good. Welcome, everyone. Today, it's a pleasure to have one of our own, Jean-Loup Tastet, who started a position here at the department last year. Jean-Loup in 2020, right? And he's now a postdoc here, as I said, and he will be telling us about feebly interacting particles and searches for detectors. So Jean-Loup.
Okay, so thank everyone for joining my seminar today. And I will take you on a journey into the dark sector. So you may be wondering, what is the dark sector? It's a generic term which denotes a set of all particles which are almost decoupled from the standard model, including, for instance, dark matter, but this can go beyond. Why do we need this? As you may be aware, the standard model has a number of limitations. Some of them are observational, such as, for instance, the prediction that the neutrino should be massless in the standard model, and therefore it cannot explain neutrino oscillations. This doesn't match the data. It also does not contain any candidate for dark matter, nor any alternative explanation. And finally, and maybe the worst, it is not capable of explaining the excess of matter over antimatter in the universe, and therefore the universe should be empty. In addition to these observational limitations, there are also some theoretical issues, such as the Higgs naturalness, the strong CP problem, the flavor puzzle, and even more. In the context of feebly interacting particles and the dark sector, I will focus a bit on naturalness, because an obvious solution to this problem would be to postulate that new particles must be light and or feebly coupled, such as they don't contribute any large threshold corrections to the Higgs mass. And therefore, these feebly interacting particles, at the very least, don't make the naturalness issue worse. And if they can explain all the observational shortcomings of the standard model, then this can be interesting theories. Obviously, this is not the only solution. This talk is structured as follows. I will first introduce you to the simplest dark sectors. Then I will describe a number of searches and experiments which are dedicated to searching for feebly interacting particles. And finally, I will discuss a number of considerations about the parameter space and the properties of such particles. Without further ado, let's start with the simplest dark sectors. You may be wondering by now, how could a light particle have evaded searches? Obviously, it needs to be a standard model singlet, which means no color charge, no weak charge, and no hypercharge. It may still interact through mass mixing, kinetic mixing, which means mixing in the kinetic term, or higher dimensional operators. And unless we are considering some rich dark sector where, for instance, some particle could decay into dark matter, a particle which coupled to standard models through this type of interaction is going to be typically long-lived. So the simplest examples of dark sectors are what we call the portals. This consists in adding one new degree of freedom along with all the lowest dimensional interactions, all suppressed by a small coupling. So just to make it clear, here are some examples. The 5 main portals are as follows. There are 4 portals at dimension 4. The first one is a scalar portal, which consists in adding a new scalar particles, which with interaction terms, which cause it to mix with the Higgs. So we have this trilinear and so dimension 3 and dimension 4 interactions. And if the mixing parameter mu and lambda are small enough, then mass mixing between this particle and the Higgs or the standard model will happen. And this mixing will be hierarchical. This produces a light Higgs with the same interaction as standard model Higgs, but suppressed strengths. We can do the same with neutrinos and obtain heavy neutral leptons. So we introduce the missing right-handed neutrinos of standard model. I don't know if we can still see my cursor. It seems to me that it had disappeared. Okay.
We can see it now.
Okay. Yes, I know what happened to it. So we can reintroduce these right-handed neutrinos, and they interact with the left-handed ones through Yukawa couplings. This Yukawa may play the role of the small parameter. Then we have the vector portal. The idea of the vector portal is that you have a new gauge boson, which could mix kinetically with the standard model photon. This is a phenomenological model. And this mixing, if suppressed by a small parameter, means that all the particles from standard model, all charged particles, would couple to this new dark photon, but with a suppressed strength. You can also do the opposite and have new particles from the dark sector, which here are represented by Xi, which couple to the standard model photon with a small mixing. And this can be implemented by coupling these particles, this new particle to a very light dark photon. There is also maybe your favorite particle here, which is the axion-like particle, which can have axial couplings to the standard model photon, to the gluon, or directly to and have axial vector couplings to the fermions. In this talk, I'm going to focus a bit more on heavy neutral leptons, because this is the portal which I am the most familiar with and on which I have worked the most. So just to give you an example, this is the standard model, with each particle as both a left-handed and a right-handed counterpart, where right-handed means SU2 singlet here in this context, except for the neutrinos. Obviously, we cannot have masses for neutrinos in this model, and the simplest extension consists in adding the right-handed counterparts to neutrinos, which are right-handed neutrinos. This enables a Yukawa term, which after electroweak symmetry breaking leads to a Dirac mass. In addition to this, because the new particles are not only SU2 singlets, but they're also SU3 singlets and hypercharged singlets. They can be self-conjugate. They have no charge at all. And this means they can have a Majorana mass term. Since we have two different mass terms, the mass structure of this sector is non-diagonal. And in order to obtain the propagating states, we need to diagonalize it. This introduces mixing between the light neutrino mass eigenstates, the new right-handed neutrinos, and the flavor states, which are the SU2 doublets, which take part in weak interactions. The light neutrino masses can be related to the parameters of these heavy neutrinos through the so-called seesaw formula. There are two interesting regimes in this formula. Originally, people considered heavy neutrinos which are much heavier than other particles in a standard model. And having very heavy neutrinos leads to light, very heavy HNLs lead to light neutrinos, which is consistent with what we observe. But as we can see, we can also obtain light neutrinos if we have small mixing angles. And this possibility is attractive because heavy neutrinos which are below the electroweak scale do not pose any problem in terms of naturalness. So to summarize these HNLs, these are particles which behave as heavy neutrinos with the same interactions as the light neutrinos that we are used to, but suppressed by a small mixing parameter. And these three conditions, they are the prototypical example of a feebly interacting particle, in the sense that we have a typically different mass, same interactions, but we suppressed by some small parameter. Why would we need heavy neutral leptons? Well, first of all, a light neutrino with small mixing angle could make a very good metastable dark matter candidate, because its lifetime can be of the order of the lifetime of the universe. Second, if we have two neutrinos and we impose an approximate lepton conservation, or asymmetry, they can form a so-called pseudo-direct pair. And such a pair can undergo CP violating oscillations before decaying in the early universe. And this can lead to baryogenesis. This has been shown by these three people. And if we combine these 2 points, then we can see that with 3 neutrinos, we can, with 3 heavy neutrinos, we can explain neutrino masses, dark matter, and the baryon asymmetry of the universe with the right choice of parameter. This is maybe the most problematic part of the model. We can go back to this later. In addition to this, I learned recently that feebly coupled particles can be problematic in the context of string theory because they can be forbidden by the weak gravity conjecture. So obviously it's speculative, but this means that by searching for this particle, we are in some sense experimentally probing string theory. So of course, it remains to be computed which exactly how small the small parameter needs to be for this particle to violate the weak gravity conjecture. So I will now move on to experimental searches. Feebly interacting particles require a number of non-trivial requirements on experiments. First of all, due to the feeble interactions, and maybe I should mention now, I'm calling this feeble interaction just to avoid the ambiguity with weak interaction. I'm talking about a new interaction which is much weaker than the weak interaction. So let's close this parenthesis. Due to the feeble interaction, the production rate is typically suppressed. In order to compensate for this, we need an experiment with a very high intensity or a very high luminosity. And with this, we also need a low background because we're looking for extremely rare events. In addition to this, these particles may be long-lived, which means they can travel a long distance from the production vertex before decaying. And in order to be sensitive to them, we may want to have a displaced detector or a large decay volume. One experimental proposal that satisfies all these requirements is the proposed ship experiment. And I'm going to start with this one because it is, in my mind, the prototypical example of an experiment dedicated to searching for feebly interacting particles. And by no means the only one. This is how the ship experiment looks. It stands for Search for Hidden Particles. And what you can see here on the bottom left corner are some happy little protons from this SPS, which are about to meet their fate in the target. And beyond this target is thick enough to make sure all the protons interact. After this target, you have a 5-meter thick wall of concrete to contain all the hadronic activity. The idea is that the only particles which go beyond this wall are muons, neutrinos, and potentially the new particle that you're looking for. In order to deflect neutrinos from the experimental cavern, SHIP is planning to have this active muon shield. This is a complicated a magnet with very complicated shape, which is designed to deflect muons of both charges, both positive and negative charges, across a wide range of momenta. away from this cavern and from this detector. And the reason this active muon shield is used is to be able to put the detector as close as possible to the target in order to retain a large acceptance. Beyond this muon shield, there are two detectors. There is a scattering detector, which is used, for instance, to search for dark matter scattering. This detector is based on some emulsion detector like Opera, but with additional trackers, timing detectors, and some more instrumentation. And then the main detector is this decay volume. This is a large volume which is evacuated, so down to 1 millibar. And the reason for this is that neutrino scattering in the air, on the air molecules, would be actually is the dominant source of background after muons. So you need to get rid of this neutrino scattering. This volume has been evacuated. In addition, there is a surround veto. So all around this decay volume, there is one veto as well as one at the beginning and one at the end, which is used to make sure that no particle can enter from the side or scatter from the walls of the experimental cavern. And the way this works is, for instance, you have a proton that scatters and produces a heavy meson, which then decays. In this case, it's a semi-leptonic decay to a heavy neutral lepton. In this case, the heavy neutral lepton mostly doesn't interact, so it goes through the detector unimpeded, and then it has a small probability of decaying inside this decay vessel. This decay looks like an appearing vertex. So a vertex that appears out of nowhere, and if you reconstruct the momentum, it will point either directly toward the target or near the target if there is some, for instance, a third neutrino. And then there is a spectrometer consisting of a magnet, some trackers, and some electromagnetic and hadronic calorimeters, which can essentially reconstruct the momentum, the energy, and identify the particles. So SHIP meets all the experimental requirements that we discussed a few slides ago. It can compensate for the suppressed production rate by having a huge number of D mesons and B mesons being produced and a large acceptance. In addition, the background rate has been validated through simulations for now, and is expected to be of the order of 0.1 to 0.3 background events over 5 years. This depends on whether we look only at fully reconstructible events or partially reconstructed decays. Regarding the lifetime, there are two detectors which are displaced from the target, and one of them is a large decay volume. So I already talked a bit about the background. And this is just a sketch of how this active muon shield looks like. So here you see the two polarities of the magnetic field and two muons with different charges and different momenta. And as you can see, both of them are deflected on the sketch. And if you average over the full muon flux, this is how the muons are deflected. And you can see that in this region here, you can place a detector. And you have background which is orders of magnitude weaker than what you would have without the shield. In addition, we can use timing coincidence to reduce the combinatorial background from these muon tracks, because the leading background is going to be so random muons which randomly form a vertex inside the decay volume. And as you will see, this is a background which is typical of these searches for long-lived particles. Combinatorial background is often the leading source of background. So a number of sensitivity studies have been performed. Here you can see on the left the sensitivity to light dark matter using the scattering detector. And in this region between, let's say, 10 MeV and few hundred MeV, it is sensitive down to the relic density. On the right, you can see sensitivities to heavy neutral leptons and to dark photons. In this case of neutral leptons, below the charm threshold, it can almost reach down to the seesaw limit, which is many orders of magnitude below even the best experiment today, which would be Na62 in beam dump mode. So before moving on to the next experiment, I think I need to emphasize something which is important to keep in mind when comparing experiments. And this is something which I think has not been advertised enough for SHIP. Whenever you have an experiment which has almost zero background, if you observe nothing, you can put a limit on the expected signal at the level of 2.3 events. This just comes from Poisson statistics as 95% confidence level. However, this sensitivity to discovery very much depends on the exact value of the background. So in the case of SHIP, if you look at the fully reconstructed events with 0.1 expected background events, only 2 observed events would represent 4 sigma, and 4 events would be a discovery. And even if you look at partially reconstructed decays, 5 events would be enough for discovery. In addition to this, thanks to the tracker and the particle identification, you can fully reconstruct the decay, the particle mass. So if you see something, you will not see an anomaly. You will be able to characterize it as being, for instance, a particle decaying to mu plus mu minus with a mass of, say, 1.5 GeV. So unfortunately, SHIP was not part of the last European strategy update. So it is currently continuing R&D and trying to optimize the design to make it more cost efficient. However, the technology developed for SHIP is already used in a number of spin-off experiments. And one of them is right now already installed in the LHC. And this is the Smd Lhc Project, which stands for Scattering and Neutrino Detector. So the idea is to take the detector, or the scattering detector from the SHIP experiment, and place it in a disaffected access tunnel near the LHC. And this tunnel just turns out to be right. It is aligned with the direction of particles going out of the Atlas detector. So it is in the line of sight of the interaction point. So here on this figure, you can see the detector in the tunnel, and Atlas would be in this direction, and particles coming there have to go through 500 meters of rock. So except for some extremely energetic muons, you will not see many particles. So this is, and of course, neutrinos. So it is very sensitive to dark sectors for this reason. It also has a very strong standard model program, because so far no experiment, at least as far as I know, has measured the cross-section of neutrinos above 350 GeV or so. Maybe phase and U will do it before, but it probes a slightly different pseudo-rapidity range. And Smd Lhc could measure the cross-sections of neutrinos at the TeV scale. And this is extremely important for experiments like IceCube, because they need this in order to reduce the systematic uncertainties for astrophysical neutrinos. So SMD can use the topology of the event and the shape of the electromagnetic shower in the emulsion in order to distinguish the 3 flavors. But contrary to phase and U, it is not. It doesn't have magnetic field, so you cannot distinguish the 2 charges. This is just an idea of the numbers of interactions that you would expect from this experiment. So regarding Bsn Physics, which is what we are here for today, thanks to the high granularity of this emulsion detector, which is accurate down to the micrometer level, it is very sensitive to appearing showers. which would be the signature, for instance, of dark matter scattering in the detector, scattering of electrons. And I think there's some ongoing study to look at scattering of dark matter on nucleons. It also has a timing detector, which can be used to distinguish dark matter from neutrinos, for instance, because if the dark matter is heavy enough, it will arrive to the detector with some time delay, because neutrinos basically travel at the speed of light, while dark matter, if it is heavy enough, will be slightly delayed due to the dispersion relation. So here's some sensitivity study which has been done for light dark matter. And you can see that it basically matches an experiment like NA64. In principle, a larger version of this could be hosted by the proposed forward physics facility, which is a dedicated experimental cavern that would be built to host several of these experiments along the line of sight of either the Atlas or CMS interaction point. Now, another experiment which can be used to search for feebly interacting particles is Na62. So this is an experiment in a CERN area which uses the protons from DSPS. So in this respect, it's quite similar to SHIP. However, there's a big difference in terms of for the detector. Na62 looks for decays in flight of counts. So the idea is that you can see at the bottom, you have a beam of kaons, which thanks to some complicated beam optics, have a very well-defined momentum. So you know the momentum of these kaons. They enter this detector and may decay to either standard model processes or, if you're lucky, to some BSM final state. Now you know the momentum of the kaon. You can measure the momenta of all the outgoing particles, and the detector is designed to be nearly hermetic, in particular to photons, to make sure that you can fully reconstruct the kinematics of the process. And thanks to this, you can reconstruct the mass of the invisible particle. So usually you just reconstruct the mass of a neutrino, which is 0. But you can look for a secondary peak in the mass spectrum. That could be a signal for a new particle. So the main physical goal of this experiment is to measure actually this K plus 2 E plus nu decay, which would look like a kaon decaying to a positron and nothing else. And that can help measure the CK matrix element VTD at the 10% level. So I proposed one study actually for Na62, which consists in looking for heavy neutral leptons produced in decays of kaons to positrons and pions. I can discuss later why I chose this particular decay, but the idea is that there is some part of parameter space which was not well covered by previous searches. So we had of the order of 310 to the 10 kaon decays for this search. And if we neglect the background, we would expect to be sensitive to mixing angle down to 10 to the minus 8, which would be close to the CISO limit, a very strong result. However, there are a number of backgrounds. The first one is that the resolution on the mass of the neutrino is finite. So you can see on this plot at the top right, you have the reconstructed mass on the x-axis, and on the y-axis, this is the number of events. So the peak that you see at 0 reconstructed mass is correspond to the neutrinos. But this is mere due to finite resolution. But this is also heavy-tailed, and this heavy tail comes from radiative photons, which are being produced in addition to these particles. And these radiative photons, most of them are going to be caught by the photon Veto, but some of them are produced with a very large angle or are too soft to be detected. And And this constitutes some irreducible background at this experiment. So the idea of the search is just to look for a bump over this smooth background. And for this, we just use the sidebands method. So we use the background in the sidebands to compute the expected background in this region and then look for an excess of events. We obtain these limits. This is a black limit with the existing data. It is much lower than, so it is much weaker than existing limits, but this is because these events have been recorded using some opportunistic trigger. There was no dedicated trigger for this final state. So with a dedicated trigger, we could improve this by more than an order of magnitude and start closing this gap. And what you can see here on the right is another limit set by NA62 for the final state without the baryon. And without the baryon, the standard model process with a light neutrino is LST suppressed, and therefore you have a much lower background. So this is all for NA62. Now, you have NA62, you have SHIP. You can combine the two of them to obtain shadows. Shadows is a proposal to reuse the technology developed for the SHIP detector, but at a much lower cost and much earlier. The idea is to put a similar detector in the experimental hole of NA62, just next to the NA62 beamline that you can see in red. So the idea is that NA62 is planning, or I think now it might have started already, to take data in beam mode. So instead of producing a K-on beam, it just dumps all the protons inside the target and then looks for displaced decays like SHIP is doing. But NA62 detector is very far from this target. So the idea is to put a near detector, which is slightly off axis to reduce the background from muons. Most muons would just go forward, while you would expect the feebly interacting particle to be produced with a slightly higher PT compared to muons. And then it's the same idea as SHIP. You observe a displaced decay inside this detector and you can reconstruct it. So it is slightly less efficient, so because first of all, it is off axis, we produce the background, but also the acceptance. And second, there is no active muon shield. And therefore you have a significant background from muons. Since it is off axis, you can still use some small magnetized iron block that can deflect some of them and reduce the background by an order of magnitude. And then the hope is to use some very accurate muon taggers, both at the entrance and at the exit of the detector, in order to reduce the combinatorial background of the muons. So here the acceptance, and you see that the muon flux can be mostly deflected to the left. So there'll be a number of sensitivity studies performed. I actually did one of them on the behalf of the SHIP collaboration. And as you can see, it is still more than an order of magnitude weaker than SHIP, but it is competitive with other proposals, for instance, like Codex B, for several benchmarks like HNL, Scalars, ALPS, and so on. So this is an interesting experiment to watch for in the near future. Now, so far I've mostly shown dedicated experiments, but you can also search for long-lived particles at the LHC. And for the past 2 years, I've been working with Atlas on a search for long-lived HNLs. And the search is not published yet, but I can still give you a very brief preview of these results. The idea is to look at...
Sorry, Jean-Loup, can you go back 1 second before you move on? So in these plots, I cannot see very well, but the SHIP lines, it is fine. The SHIP lines are there, no? I'm trying to see.
Yes, so they are in green actually.
So those are the green ones.
Yes.
Okay.
And
okay.
In this case, shadows is an order of magnitude and a half, let's say, above it. Okay. And a bit weaker above the charm threshold. So it really depends on the benchmark.
And the NA62 is the
This is the
purple
Greer's
one. Okay,
pink
yeah,
one,
like the pink.
in dump mode.
Okay. Okay, thanks.
Okay. So the idea of the Atlas search is to look for HNLs produced in W decays, which are mostly produced in a Drellian process. So it's an on-shell W is decaying to HNL plus some lepton that is observed, followed by the HNL decaying to 2 leptons and a neutrino with any combination of flavor, except taus so far. Taus are not part of this search. And the important point is that we look at HNLs which decay with a non-zero displacement. So this is made possible thanks to the large radius tracking algorithm, which can reconstruct displaced vertices with up to 300 millimeters, so 30 centimeters away from the beam axis. This is going to become standard, I think, in run 3, and there are new algorithms being developed to probe even larger D0. So for instance, without using the inner tracker, I think some ideas, for instance, to reconstruct vertices using only the muon system. If, of course, your heavy neutrino decays to 2 muons and a neutrino. This displacement greatly reduces the background because most of the standard model processes are prompt. It doesn't completely suppress it, and there are 2 leading sources of background in this search. The first one, like in the case of sheep, is the accidental crossing of lepton tracks or of tracks which are misidentified as leptons. These are the so-called multifakes. This can be estimated from data using random track shuffling. So you take a number of random events, you take all their tracks, shuffle them to obtain the combinatorial background. In addition, at lower masses and at the smallest displacement, we need to be careful about metastable standard model particles, especially if they are soft, because then they are difficult to identify. And so we have background from K-short, from heavy flavor decays, and so on. And this can be reduced, for instance, by reconstructing the mass of the displaced vertex. And in the case of heavy neutral leptons, these displaced vertex, thanks to displacement, we can reconstruct the mass of the HNL up to 2-fold ambiguity. Because we have some additional information. We have the direction of the HNL momentum. We cannot fully reconstruct it, but we know its direction. So by using cuts on the mass of the displaced vertex and the displacement, we can reduce these backgrounds a bit. One of the main issues remains the standard triggers and the default PD cuts, which are being applied to all events at the LHC, or at least at Atlas, because they are quite inefficient for light long-lived particles use soft decay products. If the particle is too soft, it is below the threshold of the detector, basically. For triggers, things are going to improve. I think Atlas is going to have software triggers, which can be, some of them can be optimized for the searches. And some experiments, I think LHC analysis, if I'm correct, are going to use continuous triggers in the future. So record all the events, and then you can perform the search with the entire data set. So here's some preliminary results of the search. This is not published yet, but Atlas already published the limits, and of course, they didn't see anything. So this is how the limits look for display search. You have here the HNL mass on the x-axis, the mixing angle. Here, this is with the electron flavor on the y-axis. And I have shown the limit for Majorana HNLs and Dirac HNLs. The upper limit comes from the displacement. Basically, if the mixing angle is too large, the HNL decays promptly, and therefore the display search is not sensitive to it. But you might have some sensitivity for the prompt search, for instance. The lower limit comes from the low statistics. And below this, there are not enough events to be distinguished from the background. And the upper limit here in terms of mass is just the intersection of these two. While at the low masses, the limit mostly comes from the standard model background. So for instance, below 2.5 GeV, there is too much background to distinguish heavy neutrinos from standard model. And the features you see here is just because we need to use a different set of cuts in this region to reduce the background coming from heavy flavor decays and so on. A novelty of this search is that we are probing not only the simplified benchmarks, so one HN mixing with one flavor, but we also probe slightly more realistic models, such as, for instance, two HNLs mixing with all three flavors. So this is consistent with the pattern of neutrino oscillation and mixing angles. And this has been done both for Dirac and baryon HNLs. I will discuss in the next section why these non-minimal models are actually important. Probing benchmarks is good, but how do we know that we're sensitive to these realistic models? And here I should emphasize that there was some workshop last year, this FIPS 2020 workshop. Actually, it's almost 2 years ago now. And the FIP community has encouraged series to come up with UV complete models instead of just portals. And experiments have a strong, really want to probe models beyond these benchmarks. So it is important to make sure that we're actually probing something which makes sense. And if we discover some particles, can we probe the model parameters or the particle properties? So as an example of more realistic model, I will use the so-called neutrino minimal standard model, which is a model of, it's still a phenomenological model. It's not UV complete yet, but this is a model of heavy neutral leptons, which can explain dark matter, neutrino masses, of course, and the baryon asymmetry of the universe. It does so by postulating that we have one light HNL with very small mixing, which is a metastable dark matter candidate, as well as two nearly degenerate HNLs with an approximate lepton number symmetry. And this one produced the baryogenesis by undergoing CP violating oscillations before decaying in the early universe. And this generates a lepton asymmetry, which is then converted to the baryon asymmetry through the Sphariron processes. But from the experimental point of view, all we have to know is that we have two nearly degenerate HNLs, which are responsible for neutrino masses, because the third one is just too feebly coupled to contribute to neutrino masses. And this already introduces some constraints because the neutrino parameters have been measured to good precision by now. And for instance, we have, if we take the constraint from UFIT and we vary all the parameters of all the new parameters of the model across all their allowed values, and we vary the neutrino parameters, the observed ones within the uncertainties, we obtain constraints on the ratio of the mixing angle of the three heavy neutral leptons with, or the two heavy neutral leptons with the three flavors. So this is represented in this triangle here. This is because it's a ratio of three quantities. It can be represented in the triangle. We have the mixing to electron flavor, to muon flavor, and to tau flavor. And the idea is that neutrino oscillation data constrains within this model the mixing angle to be within these two shaded areas. The blue one is the hierarchy normal, and the green one if it is inverted. In addition to this, heavy HNLs can be either Dirac or Majorana particles, which means they can either conserve or violate the total lepton number. Majorana HNLs can have this type of decay that you can see at the bottom left, where lepton number is violated by 2 units, which is represented by these two opposite rows in the propagator. This is like neutralizable beta decay, basically. And if you have two nearly degenerate HNL, they can oscillate before decay, like heavy mesons. If the oscillations are too slow and the HNL decays before they happen, then you can only see lepton number conserving processes, because the oscillation affects lepton number conserving and lepton violating processes with opposite phases. On the other hand, if you have fast oscillations, the effect will average out and you see equal rates for lepton number conserving and violating processes. And then your particles look like a Majorana particle. So depending on the speed of these oscillations, a pair of HN can look like a Dirac particle or like a Majorana particle. So by constraining whether the lepton number violation, you can put a constraint on the mass splitting of this, between these two particles. And if you're lucky enough and the mass splitting is between these two regimes, then you may even be able to resolve them. So let's first think about what the constraints on the mixing angle imply for our searches. And we're going to consider the prompt search, not the display search now, performed by Atlas for HN decaying to trilepton final states, which means E plus mu minus, mu plus E minus, and their charge conjugate processes. You will notice there isn't E plus E minus mu plus, for instance, and this is because we have too much background from Z decays. And therefore there is Veto on same flavor, opposite charge leptons. And as we will see, this is problematic. But in the case of one HN mixing with a single flavor, which is what Atlas initially considered, we cannot, the electron channel probes the electron mixing and the muon channel probes the muon mixing only. Now, if you have Dirac HNLs, it turns out this search is not sensitive at all. For the following reason. Due to the Veto, the only Feynman diagrams which produce these final states for Dirac HNLs, they involve a product of two mixing angles. So in the single flavor limit, so in the single flavor case, there is no sensitivity. So what I've studied is to which extent we can reinterpret these results from Atlas in order to put limits on more realistic models. And this is done by taking the Atlas results. So there are two benchmarks correspond to these two vertices of the triangle, which, as we can see, are actually forbidden within this model by neutrino oscillation data, and recasting them for ratios of mixing angles which are consistent with neutrino oscillation data. And these are denoted by all the points, all the numbered points here within these regions. So whenever you will see some numbered points in the next plots, they correspond to ratios of mixing angles which are consistent with neutrino oscillation data. I'm going to skip the actual reinterpretation. We can discuss it if you want in the questions, because it's very technical. But here are the results. I'm plotting the limits in terms of the HN mass and the total mixing angle. I use the total mixing angle for consistency because the ratio can vary between different benchmarks. In black, you can see the two limits for the single flavor case. So all of them has been recomputed in order to be consistent. These are not the ones which have been reported in the Atlas paper. They have been recomputed with the reinterpretation. And you can see that some of these benchmarks, so the limits for some of these benchmarks are much weaker than the reported limits for the single flavor case, by up to an order of magnitude for Majorana like HNLs. And the reasons for this is that in some of these benchmarks, you have a large tau mixing, which means HN may be produced, but dedicated to channels which involve tau leptons. And these are not being searched for in this search. So this is one message which we actually wanted to send to Atlas, and I think now they actually started looking at the final states involving taus in order to close this this blind spot in some sense. And we can also marginalize for all the benchmarks and obtain the gray region here, where within this model with two HNLs, it is not possible to have a mixing angle in this region, regardless of the benchmark. Results are similar for the inverted hierarchy, so I'm going to skip them. However, we see something very different for Dirac HNLs. Previously, we had no sensitivity at all because of what I discussed a few slides ago. Now, so these limits are just for reference. Now we can see that depending on the benchmark, we have some sensitivity, but it is much weaker by several orders of magnitude. Which means there exist models of HNLs which are several orders of magnitude above the reported limits. And this is something that as serious we should keep in mind. If you have a model where HNLs have an approximately conserved lepton number, they may not be very well constrained by these searches. And the way to improve this constraint for experimentalists is to include more decay channels to see if in some part of parameter space you can get rid of the veto on the same flavor, say opposite charge leptons and so on. So these few lessons that I learned by doing this reinterpretation, the most important one for us theorists is that limits reported for simplified benchmarks can't be used directly to constrain realistic models. They should be reinterpreted. This is unfortunately more easier said than done. And as part of this work, I had to accurately compute efficiencies, and it turns out to be extremely difficult. There is a method which I describe in the paper. I don't have time to describe it here in this seminar, which allows extrapolating the signal within similar models. Provided experiments report the detailed efficiencies, not for the, instead of reporting the overall efficiency, they have to report the efficiencies for each combination of diagram and signal region. With this, it is much easier to reinterpret the results. If you want to reinterpret within different model, of course, you need to implement the cost flow, which in this case I did because we didn't have this data available. But the most difficult is the modeling of the background and the uncertainties. This is almost impossible. And for this reason, I strongly urge experiments to release some sort of likelihood, either the full likelihood, or if it's too complicated, the simplified likelihood, or at least the covariance matrix between the signal regions. Without this, it is almost impossible to do a proper statistical analysis in the presence of background. If you have a background-free experiment like SHIP, you can completely skip this step 4, and it's actually much easier to report limits for arbitrary models. And this actually has been done in the sensitivity of SHIP, the sensitivity study of SHIP for heavy neutral leptons, so several years ago. Now, very briefly before finishing, I think I still have a few minutes left. I want to discuss how we can probe the particle properties, and specifically whether HNLs are Dirac or Majorana. And I will focus on the case of the SHIP experiment because I performed this study a couple of years ago. Obviously, if you have an experiment where you can measure the change in lepton number, where you observe all the leptons, then you can just look for a violation of lepton number by 2 units. If you observe this, you know that HNLs are Majorana particles. But this is not always possible. At the LHC, for instance, if there is an escaping neutrino, it can escape with some lepton number, and you don't know if the event is lepton number conserving or violating. In that context of SHIP, you can also have a charged lepton escaping, and the reason is that the decay is so displaced that the primary lepton, which is produced along with the HNL, is actually produced inside the target. And this is a very busy environment with no detectors, so the event cannot be tagged, let's say, with this lepton. So you only see the final state. And how can you distinguish lepton number conserving or lepton number violating events based only on the final state? It turns out this is possible because HNLs carry spin 1/2. And the spin is affected by the production process and will then affect the kinematics of the decay. So the decay kinematics carry some information about whether the process conserves or violates the lepton number. If you go to the rest frame or the parent meson, this is actually quite easy to see just by assuming that the light leptons, so charged leptons, by neglecting their mass and assuming that the helicity is always given by their charge. And therefore, if you have same charges or opposite charges will have opposite angular dependence in the HNL decay. In this frame, you have very clean cosine or sine dependence. However, when you boost to the HNL frame, there is a random boost which smears this nice dependence. And this can be simulating using Monte Carlo. So I did this in the context of SHIP, and it turns out that we can still see a difference between the distributions of lepton conserving and violating processes. Here in blue, you can see lepton number conserving decays, and in red, lepton number violating ones. Not only they have different distributions for various kinematical features, for instance, the energy of the HNL, the PT of the muon, for this decay of 1HL to pi L. But they also have different correlations. And using this data, we can, for instance, train a classifier, like a boosted decision tree, to distinguish lepton number conserving and violating decays. And you can see that it can have some good accuracy depending on the mass. And with enough events, we can statistically distinguish the hypothesis of Dirac and Majorana HNLs. This is the result that we obtain. So we can, for instance, try to exclude the hypothesis that HNLs are Dirac. So in some sense, we discover their Majorana nature. So we compute the number of events to exclude this hypothesis, convert it to mixing angle, and this is what is represented in this plot. You have, once again, the HNL mass, the mixing angle, in this case, is for muons. The dotted lines are the detection sensitivity in the case of SHIP and NA62. Here you can see the number of events being produced in this channel. And the black dashed line is the limit above which not only you can discover HNLs, but you can also characterize them as being either Dirac or Majorana. So there exists some region which even an NA62 will not be able to constrain, where SHIP would be able to discover HNL and characterize them. So there's been a number of studies which have been done also at colliders. I'm giving you a few references here. And more recently, there was some study in the context of Dune. Finally, if we're lucky enough that the mass splitting is of the order of, let's say, either the HNL width or the inverse of the baseline of your experiment, then the oscillation length might be of the order of the distance between your target and a detector in the rest frame of the HNL. And in this case, you may be able to observe the oscillation pattern. The way you can do it is as follows. For each event, you run the classifier on them and obtain the probability of the event being violating lepton number. This, of course, assumes that we know its mass, but by then we assume that we have enough events that we have measured the mass already. We know roughly its production vertex, it is somewhere in the target, and then we can measure its decay vertex and its momentum with great precision, thanks to the tracker. This allows us to compute the proper lifetime, and then we can bin the events with the proper lifetime, weight them by this probability of violating lepton number, and subtracting the mean. And this reveals the oscillation pattern if you have enough events. So of course, this is an optimistic case, but it is interesting to see that it is, at least in principle, possible to see oscillations even with no information on, without observing the lepton or the lepton produced in the target. So this concludes the study of particle properties and brings me to my conclusion. So what I try to show in this seminar is that feebly interacting particles are natural extensions of the standard model, which can in principle address several of its observational shortcomings. There are 5 main portals: the Scalar Portal, HNLs, dark photons, axion-like particles, and middle charge particles. There's a number of currently or proposed experiments which are already probing these particles, and more are going to join this search. And these experiments are usually referred to as intensity frontier experiments because they are designed to search for rare events. This includes the Smd Lhc and even run 3, thanks to these dedicated triggers, large radius tracking, and so on. But as serious, we're also interested in models which are more realistic than these 5 simplified benchmarks. And in order to do this, to set limits on these models, we need to do reinterpretation. So far, this reinterpretation is possible, but quite tedious. So it is important if we want to be able to constrain our favorite models to, let's say, press experiments to release enough data and sufficiently fine-grained efficiencies, as well as likelihoods, in order to simplify this interpretation. I also want to re-emphasize that when we compare different experiments, it's not enough to just compare the expected exclusion limits, but also their discovery potential, because an experiment with a great discovery potential can make the difference between just seeing an anomaly and making a 5 sigma discovery. And in the same spirit, it's important to, to characterize particles, to know if we've observed some unaccounted background or some HNL or some scalar and so on. And finally, as serious, we want to go beyond this portal and test UV complete models. And experiment would be very interested in hearing about your model. So if you have a model which can explain, I don't know, the strong CP problem of flavor and which involves some feebly interacting particles, please get in touch with experiments. There is currently some strong interest in probing these models. So thanks a lot for your attention. And if you have any questions about the dark sector, feel free to ask.
Thank you very much, Jean-Loup. It was a very interesting seminar, a very clear overview of the state of the art about freely interacting particles. Pilar must leave, but here I am co-hosting the meeting. So shall we start with the questions?
Yes, please go ahead.
Any questions from our audience?
Well, I thank you for that talk. It was very clear. I would like to know more about what you skipped about, how you did the recasting of the constraints. But if it is too technical to do it now, we can discuss it at any other time.
This is fine. So I have some a slightly scary slide about the reinterpretation workflow. So the idea is the following. We take I don't know if you can see my cursor, I think it disappeared again. I cannot show it for some reason. Okay, I will use the laser pointer. So we digitize the signals and the various background components from the paper. And we also had to look at the PhD thesis of the PhD student who did the analysis, because the detailed uncertainties on the background were not reported in the paper. So this is already an issue. Something that in the future people should include in the papers. We don't have to look at PhD thesis. So from this, we extract the observed counts, the expected background, and knowing the background uncertainties and the expected background, we make a simplified background model. And this background model, we try to validate it. It's actually just a very complicated exercise, but we tried several models until we basically obtained the same limit as Atlas. So this is, here there is no, the signal counts that we use for this plot are exactly the same as for Atlas. So this, the only thing that changes is the way we model the background. So the difference between, so the yellow and green limits, which are the original one from Atlas, and the ones in inverted colors, the one that we obtained. This is the best case, the most accurate background model that we could make. So now going back to this chart, we still miss the signal because based on we need in order to perform statistical test, which is the CLS test, we need the background model, the observed counts, and the expected signal. To obtain the expected signal, we used a math graph to generate all the relevant diagrams. And the reason we have to do this is that Atlas did not include all the relevant diagrams. For instance, the diagrams with mixed couplings, both electron and muon, were not included in the original analysis. So we had to simulate them from scratch again. And we also had to re-implement the intercut flow. And this we did with quite some success. I mean, we obtained fairly similar efficiencies. These are the efficiencies that we obtained. I think this is for lepton number, this one for one specific, these are for the 4 lepton number violating processes. So as you can see with twice the same flavor and charge for the first lepton. So what I'm showing here is, as function of the HNL mass, we had 5 mass hypotheses, and I show the cumulative efficiency after applying all these cuts in order. So we have displacement cuts, PT, eta cuts, then we apply the trigger, trigger offline requirements, some lepton isolation criteria, some Z-Veto for the electron channel, some requirement on the mass of the 3 leptons, and some missing energy cut. So some of these, I think the loose requirement, we use some tabulated efficiencies. While for the other ones, we just generate the events and then we apply the cuts. And as you can see, at least on log scale, we obtain roughly the same efficiencies. The worst case, I think, is here for this process, but it's overall quite accurate. So knowing these efficiencies, so here we are here, this cut flow. We have simulated all these diagrams separately. Then, knowing the model parameters, we leverage the scaling properties of each diagram. And here, I think I can go back to this. Wait, I think this is the slide. For each diagram, we know, for instance, for this process, the 2 particles which couple directly to the HNL are electrons, and therefore, the cross-section of the signal scales as the electron coupling squared for each diagram, and therefore for the total process, we have electron coupling to the 4th power divided by the width. And this is because of the, we have the cross-section is equal to the production cross-section times the branching ratio, which is the partial width divided by total width. So each diagram has a scaling relation like this. In this case, we have 2 different mixing angles. So using this, we rescale for each mass hypothesis, not just for each hypothesis, both in terms of mass and benchmark. So for each set of model parameters, we rescale the signals. And then we apply a further rescaling if we have Dirac or Majorana HNLs, because this affects the width and it affects the cross depending on whether we have 1 or 2 HNLs. For Dirac HNLs, the lepton violating processes are suppressed, and the lepton conserving ones are coherently enhanced, for instance. So we perform rescaling based on mixing angles and Dirac-Majorana nature. So we obtain some, let's say, knowing the efficiencies, the cross sections, the efficiencies, we know the efficiencies for each channel and each bin. We can obtain the expected signal in each channel and each bin on a per process basis or per diagram basis. Then we sum everything to obtain the expected signal. So knowing the signal, the observed count, and the background model, we perform the CLS test to obtain the limits. And then we iterate this. Typically, we fix the ratio of the 3 mixing angles, and we leave our free parameter is the total mixing angle U total squared. And based on this, we obtain these limits that were shown in these plots.
So I guess that the only alternative which is not a good one, but to all the work that you did in order to estimate the backgrounds and efficiencies and so on, would be to assume, for instance, that the limits that Atlas was giving in each of the mixing angles, in the one with the electron and the muon, were, say, Gaussian distributed, and then with those you would have an estimation of the bound on the electron mixing and the bound on the muon mixing, which you can then use the rescaling. And I think a lot of people would have done that. It is not statistically justified, and probably you would get something very different. But I wonder what would be the outcome of that exercise compared to yours, to see how bad that approximation is.
So I think actually we had a master student doing this, and it works for most benchmarks, but sometimes it catastrophically fails by more than an order of magnitude, for instance.
Okay, and did you understand what made the ones that failed catastrophically fail so much, in order to see if there is a pattern?
If one mixing dominates, it's actually quite complicated, but if one mixing dominates compared to the others, then this approach works, because we're basically taking just the best limit. But if we have a mixing,
because then you are not extrapolating far from the limit of Atlas.
Yes, exactly. And some particularly, the most difficult thing is that the two channels, they are some correlated. Some of the backgrounds are actually correlated, because the background they have common uncertainties or common nuisance parameters, and therefore, in principle, you would vary this background, these nuisance parameters simultaneously for both of them, and this is a nightmare. So there's actually a better method to do this, which is basically to ask experiments to report instead of having to compute ourselves.
But you did not have that information.
Yes. We're trying to push Atlas to do this, but there is a lot of inertia. I mean, even the new analysis, which I just of which I saw some excerpts, will not contain such information. So this is some far future plans.
Okay, thank you very much.
Hi, I managed to come back. Thank you very much, Jean-Loup, for the nice talk. It's already a little bit late. It's getting a little bit late, so I would ask people if they have further questions and follow up. Remember that Jean-Loup's office is in the 3rd floor, very close to the kitchen.
Yes.
So please feel free to continue the discussions live and hopefully in person. Okay, thank you very much, Jean-Loup. Thank you, Rosa, for handling the questions at the end. And I will close here, okay? Thank you.
Okay, see you all.